All right, work in angles, 5-3. On the worksheet, you're just going to do number 1 and number 2. So, this is something that you'll find we're able to put together information from the past chapters. It ought to make sense pretty good on how you're doing it. Now, there's an equation on the paper for 5-3. Work equals a force parallel to the direction of motion times the displacement, or the distance it went. It's really the displacement is going to be, it's always going to be in a straight line this time. Even if it's at an angle, it'd be a straight line up the ramp, or down the ramp. There's another equation that says F cosine theta d, and I did use that for a while. You might see it on some answer keys, but I don't prefer that equation. I think it's better not to do that. It's better to draw a diagram and then to use draw a diagram and then look at what's needed in the picture to do the problem. Okay, so for letter A it says a raccoon pushed a raccoon is pushed a distance of 21 meters along the floor by a 575 Newton force applied from 63 degrees above the horizontal. So I don't know if I can draw a little mapache right here, and the ones, it's like a taquache, but he has like a mask on him. Okay, so there's a little I don't know what he is. Maybe it's a little baby raccoon. Ooh, they should be they're bigger than that, or a lot bigger, aren't they? They're kind of fat. And don't they have that tail that does like that too? Yeah, something like that. Oh, whatever the case is. Oh well. Actually, his tail might be in the way, so let's put it this way. All right, so we're going to push him with a force. I'm going to put a force right here. It says, so there he is. He'd be sliding along. You're pushing the little thing along by a 575 Newton force. So 575 newtons pushed at an angle of 63 degrees above the horizontal. What that means is the horizontal is like the X. Sometimes they even say at 63 degrees above the X-axis. So that's 63 degrees. I probably should use a different color there. Oh, well. Oh, here it is. I can do it quick. All right, at 63 degrees above the horizontal. That doesn't look too neat, okay? Okay, 575 Newton force. All right, so, really, I guess he'll be more like snug to the ground, won't he? He wouldn't be on his feet. So he's kind of like, lying down. This looks, I don't know what this creature looks like on here. It looks like a cat or something, doesn't it? I don't know. Oh, well. Whatever it is, I just want to make it more exciting. Push a little taquache instead of like a brick or something this time. So we're going to push him along on the ground. Now it says that he's pushed a distance of 21 meters. So from there all the way to here, 21 meters, that's a long way. It's like over 20 yards. That's the distance, displacement. And they want to know how much work is done by that force. All right. Well, so probably that the key to the question is it's the force parallel to the direction of motion. So that means I got to find my Fx and my Fy. You don't need the Fy here yet, but a lot of times when you see a triangle, you might want to just go in and figure out Fy and Fx. You'll see why that might come into place. But first we'll get Fx. So we know that sine of 63 will give you Fy, cosine will give you Fx. So that's why the cosine comes into play. I'll put that first. Cosine of 63 is equal to Fx over 575 newtons. So that means that also the other one, sine of 63, oh boy. Well, I guess I'll have to put it down here. My picture was too crazy. Will be Fy over 575, okay? So cosine of 63, 0.453, 5 times 575, so 261. So Fx, 261 newtons. 63 sine times 575, it's 512 newtons for Fy. Now, you'll see, they didn't ask you to find these yet. Well, you had to find Fx, because this is the force component that is parallel to the direction of motion. Didn't look too parallel how I drew it, but that's Fx. So only that part is going to be pushing him. You know, it's interesting, and when you think about it, if you stand right behind something and you push forward, then all your force is going into doing work on the object. But when you push it at an angle, you're actually not. You could actually make it harder for yourself because of friction. Because think about it, you're pushing it down. Part of it is getting downward pushed into the ground, right there, Fy. So that's pushing him closer to the ground. So it's actually making it a little bit harder to slide him if there is friction. Now, we ignored friction on this part, but later it'll come back, and that's why I'm doing this part now. So for the first part A, just to find out the work done, it'll be work, force times parallel direction of motion times the distance. And the force parallel direction of motion would just be Fx, which is 261 newtons times 21 meters. Sorry, okay. So 5480, if I use sig figs. See, I round off the three significant figures, 5480 joules, and it will be positive. I told you, well, we should always let the direction that it goes be positive, and that'll make things easier. Okay, now, is my video, is it coming down a little bit? Sometimes, sorry about this. Let's see if that works better. Okay, yeah, this thing, have a little stand here. Okay, so that was part one. Part two says, if the raccoon's mass is 30 kilograms, so if he weighs 30 kg for B, all right, and then, actually, we should remember this, that for A, the answer was 5480 joules work done by Fx. All right, that's how much work is done by Fx. All right, now for B, it says if his mass is 30 kilograms and if mu k is 0.050, then find the work done by friction and the net work done. The work done by friction and the net work. So we got to find we know that there's friction now because they're telling you that. So friction will always be opposite the direction of motion in between the two surfaces together. So friction will be going that way. F friction. So let's find out, first of all, what is the friction force? So friction force, you can remember. That's why I kind of like doing a little bit of this chapter because it reviews the last chapter. It's the coefficient, but also times the normal force. The normal force we're going to get from getting his weight. Okay, or, well, and you'll see. So 0.050, mu k equals 0.050. So his weight is mg. That's going to be 30 kilograms times 9.81 meter per second squared. Now you can make it negative if you want to. Let the weight be negative. 30 times 9.81, 294, negative 294 newtons. Now, his weight is pulling him down. Is his weight equal to the normal force? Well, and I know I use all these arrows here. So you have this force, 1, friction, 2, weight, 3, 4, normal force. In this particular problem, the normal force is actually not equal to the weight because you also have Fy, pushing down. So the normal force, since he's not going through the ground, he's being supported. So that means that this force must equal both his weight and the Fy. So Fy and the weight. So the normal force, I can make a net force equation if you wanted to, but I'll just do it this way. But I think you can see the normal force equals, it'd be the opposite, but equal to Fy and F weight. Fy is actually negative 512. We know it's going downward. So then the normal force will be the negative of negative 512 and plus negative boy, all these negatives are going crazy. 294. But really, this is just, you don't, if you just put 512 plus 294, that's okay with me on your paper. But remember that, okay, if I put brackets around this, if I add Fy plus F weight, they're both negative. Negative 512, negative 294. 512, 294. I get 806. Negative. Well, the normal force has to be opposite the sign of this one, so it's positive 806. You don't have to show me all the negatives when you're doing it. If you just want to say 512 plus 294 is your normal force, you know, if you draw a diagram, it'll be obvious how you got that to me. Okay, so wow, all that work to get 806. So make sure I did that right. 30 times 9.81 plus the Fy. Is Fy 512? That's pretty amazing to me. 806. Yeah, because it was a big angle. Sine 63 times 575. I was double checking it. Yeah, that's correct. Okay, so now here we go. Back to the friction force. Friction force. Let me move it over because it's going to be such a mess here. Force of friction is mu k times a normal force. So 0.050, that was the constant for friction, times a normal force 806 newtons. So your friction force 0.050 times 806 is 40.3 newtons. 0.3 newtons. So friction force, well, actually I can just keep it there, I think. I think we'll be okay. Well, maybe. We'll see. Friction force is 403 newtons. Now, what is the work done? It says, the last question, what's the work? Okay, what is the work by friction? I didn't answer the question B all the way yet. B is a long one. Find the weight, find the normal force, find the friction force. Then the work done by friction is going to equal the friction force times the distance. Okay, so the friction force is 40.3. Now, actually, it'll be negative because it's going the other way. So negative 40.3 times the distance, 21 meters. Newton times meter. So it's 846 joules. Negative 846 joules. 40.3 times 21, negative 846 joules. So, negative 846 joules is the work done by the friction force. Okay, negative 846. So, you might have to go back, or you can look back at that if you want to. Remember, to do B, we had to do a lot of stuff to find the work done by friction. First, we had to find the weight of the raccoon. Then we had to find out what is the normal force, and we know the normal force is equal to both the weight plus the Fy, 806. Then we take the normal force and put it in the friction equation to find out the friction force. Once we know the friction force, now we multiply it times the distance to get the work. And work has to be negative, just like friction has to be negative, because it's opposite direction of motion. All right, then the last part, this really should have been a C, but it's on B. What is the net work done? Okay, so B, I'll just call it B part 2 or something. Net work. The net work. All right, the net work is equal to the sum of the work done by every force. So the work done by, actually, Fx plus the work done by F friction. And so Fx, the work done by Fx was 5480 joules. The work done by friction is negative 846 joules. So you're subtracting them. I like to just always do that, to be careful. Now see, one thing I'll tell you, remember that time I mentioned to you, always let the direction you go in be positive and the other will be negative. So just think about what the forces do, and the work does the same thing. So like, if the force is positive, the work has to be positive. If the force is negative, then the work will be negative. Okay? So just put, you can do that. One sign will go in front of the work. Because once I was telling you, should you put positive, negative for the force or for the displacement? So these have to match. These have to be, well, I won't say, that might be confusing too. I'll just say there's only one sign that you put in there. You never have negative and negative. If you ever have negative for that one and a negative for that one, if you put them in, you're doing something wrong. Only one negative should be in that. Okay, but anyway, 5480 minus 846 is 4634. Or just 4630 joules. That's the net work being done. Okay, there it is. That is the one problem. Wow. So when you do number one, if you wanted to stop and do number one now in the homework, you could do that. Number one is just like this problem. Very similar. Then I'll show you one like number two. Okay. Now, B, actually B is, you know what, I'm still having a problem with this thing. I guess it's just not tight enough. I have a little clamp on the side. I'll try to get it. Okay. B, how much work is required to lift a 20 kilogram brick to a height of 9.37 meters straight up above the ground? Okay, so this problem is not anything with angles. The work equals the force, parallel times distance. So if we just go straight up, 9.37 meters, and the brick is 20 kilograms, then we got to figure out the force and the distance. The force would just have to be the weight in this case. So it's 20 kilograms times 9.81. 20 times 9.81, 196 newtons. So the work will be 196 newtons times, it went up 9.37 meters. (1840 joules). So 1840 joules of work. 1840 joules of work. Work equals that. I ought to say work. By, it was done in lifting that because you had to match gravity as you pulled it up. All right. Well, that's gonna kind of come into play in the next one. For C, it says this: how much work will be required to push a 20 kilogram brick? Now we got a 20 kilogram brick again. 20 kilogram. Oh no, and I took away my answer there, but oh well, we'll get it in a second. I can find it again. 20 kilogram brick to a height of 9.30. Oh, I'm sorry, I read the wrong question. How much work is required to push a 20 kilogram brick a distance of 14 meters up along the surface? Oh yeah, there he is, my computer. Up along the surface of a 42-degree incline. So this is 42 degrees, and we want to go up. It says a total of 14 meters. So we'll just say this whole thing is 14 meters all the way to there to there. How much work is required to push it up the incline? All right, so for this one, we're going to have to draw our little diagram. And I'm going to have to do two things at once because my computer has had a problem, and I'm going to be okay with it, I believe, now. If that's 42, then that's also 42, the angle, theta. Now, this is F weight, and we already figured that out. That was 196, right? 20 times 9.81. It's already on your paper, 196. F weight is 196 going down. But what is Fx and Fy? Only Fx is actually doing the work. And so now you can use sine of theta is equal to Fx over the weight. So I'm kind of jumping without writing the equation. So work will be the force parallel direction of motion times the distance. The force parallel will have to be Fx times the distance is 14 meters. So we're going to find Fx, and sine of 42 will give me Fx over the weight so 1 Fx over 196 newtons. It's 131 equals Fx. So Fx is 131. So 131 newtons applied to get it up the ramp a distance of 14 meters is going to be 30 joules. Now, the interesting thing is, well, you'll see, 1840, they're pretty close, 1840, because it's actually going to the same height. It should be the same number. Maybe they're close. It's about 131 times 14, 1834. It's almost 35. You could actually say, if you want to say, we'll just say it's 1840, but I mean, it's 1840. I rounded it, 34 actually. It's really close to that one. Well, the reason why this is significant is, look at what you can also do if you want. If I wanted to find out what is the height of this thing, I can find out the height simply by knowing if this side of the triangle is 14 and it's 42 degrees, well, forget the middle part. Sine of 42 would be the height over 14. So, sine of 42 times 14, you don't have to do this. I'm just doing an extra little step here. Sine of 42 times 14 equals 9.36 meters. No, 9.37 meters. Now, why is this interesting? Think about the problem I did right before it. 9.37 meters, and it's 20 kilograms. Remember the problem before it? 20 kilograms, we lifted up 937. Well, it's the same amount of work. They should be the exact same number. It's just only because of sig figs. That one said 1830. That one could have as well have been 1830. But they are matching, because if you want to put that brick and lift it up 9.37, you have to put its full weight force. You have to lift with its full weight, which was 196 newtons. 196 newtons, you got to lift it all the way up to the top, to that highest point, 937. Or, instead of that, you can take it and slide it up a ramp, and then you only have to push upward with 131 newtons. So look at that, 196, 131. You push a smaller force, and you have to go a smaller force on a longer distance, but you get the same amount of work done. So, just do number 1 and 2. If you want to try number 3, that's a great challenge one. It has an angle, and it also has friction involved. But just do number 1 and 2, but do all of number 1. So it's kind of like you're doing 3 problems anyway. Number 1, but with and without friction, and then you're doing number 2. All right, thanks a lot. See you.